How does your electricity get to you? You might think that it comes from a large power plant, like the Trottier Falls Dam, down to Montreal before being distributed to your homes. But that's not quite true. Your power actually comes from that large dam to over 30 neighborhoods all over Montreal. And your power actually comes from multiple large dams, all connected to the same 30 neighborhoods. Now, with the integration of renewable energy, we're starting to see more and more small power plants, like wind and solar farms, scattered across the province. And these small power plants are of course connected to the same 30 neighborhoods. Now, let's take a look at this complex power system and assume that it's experiencing an extreme weather event which damages just one of these transmission lines. Which transmission line do you think would have the largest impact on the system if it were to be damaged? If you're like me, you might think that it's one of these transmission lines. After all, we do get most of our power from these large generating stations. If that was your initial thought, then you might be surprised, just like I was, to learn that it's actually one of these transmission lines whose outage causes the largest blackout. My research focuses on reducing the size and impact of these extreme blackouts. To do this, we can build a model of this complex power system. And using this model, we can assess the response of the system to hundreds of thousands of different blackout scenarios. From these results, I can compute an index for each component. If the value of that index is high, then I can tell you that that component contributes significantly to extreme outages. Well, if the value of that index is low, I can tell you that it contributes negligibly. This simple approach has one glaring problem. It's just really slow. My goal was to speed that process up, which I accomplished by applying the polynomial chaos expansion method. The polynomial chaos expansion method aims to approximate the response of the system using a simple function that looks like this. Computing this function entails determining these orthogonal basis functions and the corresponding coefficients, which I can do using just 100 evaluations of my blackout model from before. Now, if that was a little confusing to you, that's okay, because the important part is this. From these coefficients, I can directly compute the same indices from before, and should, theoretically, be able to tell you which components are the most critical. Now, to make sure that this worked, I went ahead and tested it. I modeled the response of the power system to an extreme windstorm. Initially, the resulting outage affected over 1 million people. By applying my method, I was able to identify just 2 critical transmission lines in the power system. By strengthening these lines, the resulting outage now affected just 130,000 people, all by strengthening just 5% of the components in this transmission system. While current methods exist which could identify the same improvement, it would take them over 21 days to give you that answer. Well, my method can do the same thing in just 1.5 hours, turning a problem that needs a supercomputer to solve into one that can be solved on your laptop. Using this method, power system operators will be able to efficiently identify critical components in power systems, directing infrastructure investments to maximize their impact. They will be able to design power systems to withstand the extreme storms of our future.